So in this video, we are going to look at the law of sines and cosines. Many of you have maybe seen this before already in geometry, but I'm going to show you the best proof of the law of sines and make more sense of what the law of sines actually means. I'm going to be looking at the standard proof of the law of cosines. Nothing special there, and then we'll use them a few times, and then I'll have you guys play around with them at home. So without hesitation, let's go ahead and get started. All right, so the law of sines and the law of cosines are great for solving triangles, determining the angle and the side lengths of triangles that are not right triangles. If it's a right triangle, right triangle trigonometry, Pythagorean theorem, we're done. But law of sines, law of cosines, great for triangles that are not right. So what we need is a triangle that is not right. So let's go ahead and get that. Cool. There's one side. There, let's go ahead and there's another side. And there's the final side. Cool. All right, so there's a triangle that is not right. So I need some sort of relationship between each of these sides. So I'm going to go ahead and give each of these sides a name. So I'm going to call this C. I'll call this angle C. I'll call this B. I'll call this angle B. And I'll call this A. And I'll call this angle A. Cool. All right. So I need to relate the sides and the angles in some way that use the sine function. So the height, the opposite and hypotenuse sides of a right triangle. So we need a right triangle. Before I do that, actually, I'm going to be a little bit sneaky, and this is what makes this proof so beautiful. And I'm going to give myself a circumscribed circle. Let me get a little bit better than that. Cool. Why did I do that? Well, the diameter of a circle has a very interesting property, and that is if I connect it to an arbitrary point on the semicircle, all right, the traversed the arc that is cut by this diameter, that is a right angle, and I have myself a right angle, thus bringing up the law of sines. The sine function. All right, look at this thing. All right, what can I come up with here? This angle right here, right? What is this angle? All right, take a second to think about what it is. All right, it is the same as angle A, angle C, All right, this is the same as C. I'm gonna go ahead and call it C prime. All right, it is C. I'm not even gonna call it C prime. It is C. It's the same C, the measure of angle C. All right, and so with that said, the law of sine says the sine of C is equal to opposite over hypotenuse. So C, little c, length C, over the diameter of the circle. That's nice. All right, but what can I do else with that? All right, watch this. Same idea. Let's get a diameter starting at angle A, going through the center. Of course, it's diameter. And then going to C. What happens now? All right, we have another right triangle. I'm a little bit off. Sorry about that. We have another right triangle. Right? And what is this angle measure? Right? This is the same measure as angle, let's see, B. Right? B intercepts this arc, and this angle intercepts the same arc, so it is the same as B. All right? And with that said, I can go ahead and I can say sine B is equal to opposite, which is B over the diameter. And you may already see the law of sines. All right, if I reciprocate both of these, or more importantly, if I solve for d in both of these, I'm going to get d is equal to c over sine c, and I'm going to get d is equal to b over sine b, length b over sine of angle b. And there it is, or there it is partially. We have b over sine b is equal to c over sine c. All right, but why is this far superior to any other proof of the law of sines? It's also equal to the diameter of the circumscribed circle. Right, that's really cool. If you have a triangle, right, and you have the law of sines, right, the law of sines not only does it equate the side lengths and the angles, but those ratios are also the diameter of the circle traversing through each of the vertices of the triangle, which might be a very useful tool in the future. We'll see if that plays a role later on, right? But we have b over sine b is equal to c over sine c, and then also that last one, a over sine a. So maybe you've seen the law of sines before, maybe you haven't, all right? But regardless of the triangle, all right, right triangle or not, all right, a over sine a is equal to b over sine b, which is equal to c over sine c, which is a useful tool. I'll leave it to you guys to prove this little bit right here. All right, why is this also equal to these two things? Let's do a quick example. So, here's a triangle. And you're going to have an angle of 51 degrees. You're going to have an angle of 40 degrees. And you're going to have an angle of 10 centimeters. All right, so we want to solve this triangle. We want to find all of its sides. All right, we can't use the Pythagorean theorem because none of these angles are 90 degrees. All right, that is a 40. All right, so how do I do this? We have the law of sines. So a divided by sine a is equal to b divided by sine b, which is equal to c divided by sine c. All right, cool. So letters don't really matter. What's important is that these are the same letter, and these are the same letter. So right now, immediately, I can use the law of sines to find this side. Letters do make things nice, though, so let's backtrack and give ourselves some letters. Let's go ahead and call this B, we'll call this A, and we'll call this C. So we're looking for side C, and we're looking for side A, and we're looking for angle B. Angle A. All right, so can we get side A or angle A right now? No, we cannot. Right, because we have none of this information. Right, we cannot generate an equation with one unknown. Right, but we can get C, so we're going to jump and get C, or we could get angle A immediately. It's up to you. Right, I'm going to go ahead and get C since it's possible. So we got 10 over sine 51 is equal to what we don't know, which is C over sine the angle that we do know, 40. So we just need to solve this. C is equal to 10 sine 40 over sine 51. And that is equal to, make sure you are in the right mode. We are working with degrees right now. 8.271 centimeters. All right, so this is 8.271 centimeters. I highly encourage you to leave this number in your calculator as you proceed, so that you can have the most accurate possible answer at the end. All right. How can we get this side? Let's go ahead and just use the triangle sum theorem. All right, the sum of the angles of a triangle will sum to 180 in a Euclidean geometry. So 180 minus 51 minus 40 is 89. So this is 89. Very close to a right triangle, but not a right triangle. All right. Okay, cool. And so let's, we have 1, 2, 3, 4, 5. We just need A, which means we need to use the law of sines one last time, especially now since we have 89. A is going to be, or more specifically, let's do it out. A over sine 89 is equal to, I'm going to go ahead and use B since all my numbers are whole. So we got 10 over sine 51. So A is, what is that going to be? 10 times sine 89 over sine 51. Sine 89 is going to be really close to 1. 10 sine 89 divided by sine 51 is 12.866. All right, we were able to do this problem because we had a pair of sides. So we had B and capital B and lowercase b. And we were given an angle so we could find C and we could proceed. So in this case, we were given the triangle pattern of angle, side, right? So we can use the law of sines to solve angle, side triangles. Let's go ahead and write that down real quick, all right? Law of sines, we can use law of sines in angle, side. So I don't want to do any more examples, but I do want to look at the patterns. So let's look at the other patterns that prove triangle congruence. So let's look at a side angle side example. Let's look at an angle side angle example. Let's look at a side side example, and let's look at a HL example. All right. So side angle side. Let's give ourselves like an example. Here's a triangle. A, B, oh, I want that capital A, B, C. All right, cool. So side angle side, that means we have two sides and an inclusive angle. So let's go ahead and say this is 10. Let's say this is like 70, and let's say this is like 9. Cool, side angle side. So can we use the law of sines here? And the answer is, think about it for a second, all right? But the answer is, well, let's write it out. We have A, 9 over sine A. We have, what is that? B over sine 70. And we have 10 over sine C. All right, and there's the problem. All right, we have three expressions here, all equal. But no matter which two that you choose, there will be two unknowns. All right, if you choose this one and this one, you'll not know angle A, and you won't know side B. If you choose the first one and the third one, you'll not know angle A, but you also won't know angle C, and so on and so forth. You cannot determine the sides of this triangle or the angles of this triangle given the law of sines. So side angle side does not work. Okay? How about angle side angle? All right. Let me change the color here. Angle, side, angle. Can we use the law of sines here? All right, quick example. All right, angle, side, angle means we have an angle. So let's go ahead and say this is like 30. Let's say this is like 70. All right, and then let's say this is like, I don't know, 6. All right, it doesn't really matter. All right, can we use the law of sines here? So let's go ahead and call this A. Let's call this B. Let's call this C. C, B. All right, 6 is equal to A. All right, let's write out the law of sines here. So we got 6 over sine A. We got B over sine 30. And we have, that's a B, and that's a 6. 6 may not have been the best number to choose. And then we have C over sine 70. All right, cool. So one might quickly say that we can not use the law of sines here because if we set any of these two equal to each other, we will have two unknowns in each. However, when given angle side angle, you're given two angles, which really means you're given the third angle. All right, so 70 plus 30 is 100, so that means this is 80. All right, so we actually do know A. So we do know this, and then now we can use these two equations to determine B and C. So it does work here. It does not work here. All right, let's look at side, side, side. All right, you might already know the answer. All right, side, side, side. All right, here's a triangle. We know all the sides. 4, 5, 6. Cool, not a right triangle. Perfect. All right, so we know 4, 5, 6. And that means we have the numerators of each side, 4, 5, 6. And then we have sine A, sine B, and sine C. And I'm going to be a little bit lazy on this one because we cannot use the law of sines. There's no way to get A, B, or C, angle A, B, or C with the information given. And because of that, we cannot equate any of these and have one unknown variable. So it does not work here. We cannot use the law of sines here. And then last but not least, HL. You might have been staring at this one the entire time. We definitely can solve this one, and we do not even need the law of sines. We don't need the law of sines, and we don't need anything else that's new, because HL implies that this is a hypotenuse. You're given this. Let's go ahead and say this like 8. And you're given a leg, so let's go ahead and say this is like 6. All right, you know what? Let's go ahead and make this 10 and 6. All right, now it's the right Pythagorean triple. All right, but this is a right angle. So even though we don't know any of the angles, we do know that this one is 90. And while this is angle side side, we can use the Pythagorean theorem. So we don't even need it. All right, I'm going to put an X here because we don't even need it. All right, so angle side angle and angle angle side are when we use the law of sines. All right, so we need something new to get the law of to get the other ones. We want side angle side and side 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 here. All right, HL is just the Pythagorean theorem. What is that thing? That thing is the law of cosines. All right, so let's get the law of cosines out here. So there's a standard proof that I'm gonna show you guys to justify the law of cosines. Nothing special to this one. You may have seen this one before. All right, but if I give you a triangle, all right, with sides C, B, and A, and angles A, B, and C, you can drop an altitude from one of your sides, from one of your vertices, messing up my language all over the place, and then generate two right triangles that you can then get the law of cosines out of. All right, so what does this mean? All right, so if this whole thing is A, then let's go ahead and call this side right here X, which would make this A minus X. Why is this the move? Because now we have some right triangles that we can work with. What equations do we get from these right triangles? Well, we get 1, x squared plus h squared equals b, h being the height of this triangle. And we also get a minus x squared plus h squared equals c squared. So we have these two things. And if we can somehow solve this system of equations, all right, by eliminating x and h, if we can relate these somehow, we will have an equation that has b's, a's, and c's. That'd be cool. All right, so let's play around with this thing. All right, I'm going to expand this bottom equation. So we're going to get a squared minus 2ax plus x squared plus h squared equals c squared. Cool. All right, and if you don't see it right away, look at this thing and see if anything's familiar to you. Does anything in here look familiar? All right, that x squared plus h squared is right there. All right, x squared plus h squared is b. All right, so now we have this. Oh, sorry, not b squared. All right, and then so we have a squared minus 2ax plus b squared equals c. Now all we need to do is eliminate x. We've gotten rid of h. All right, what's x in terms of things that we know? This is where the the cosine ratio comes in handy, right? Because a cosine of c is equal to x over b. All right, things we know. And then if I multiply by b, I get b cosine c is equal to x. Let's go ahead and plug that thing in. All right, here is the law of cosines. All right, a squared minus 2a, we just found out that x was b cosine c, plus b squared equals c. Right? The law of cosines is this. Oh, I keep messing that up. That should be squared. Squared. The law of cosines is right? Given a side, c squared is equal to the other two sides squared and summed, kind of like the Pythagorean theorem. But then there's this like error, 2ab cosine c. And if we had chosen a different side, it would have been, let's go b squared, right? We'd have a squared plus c squared minus 2ac cosine b. And if we had chosen a squared, it would be equal to b squared plus c squared minus 2 bc cosine. Yeah, for cosine a. All right, so there is your law of cosines. All right, and it just depends on which side that you do you want. What information are you given? All right, can the law of sines help us solve side angle side or side side side? Let's check it out. So here is an example of side angle side. All right, I give you a triangle whose sides are a equals 11, b equals 5, and angle c equals 20 degrees. All right, what does that triangle look like? We have two adjacent sides and an angle that is between them. So A, B, and the angle between them. So we're going to go ahead and write 20. A is 11. I'm going to make this a little bit bigger than the B because B is only 5. Right? So my B is about half the size of my A. Right? A equals 11, B equals 5. Then I have this other side. Right? That's going to be our C. Right, so we have angle C over here, angle B over here, and angle A over here. Cool. So how do we solve this thing? Can the law of cosines do it for us? Well, we have, we don't know C, but we do know A, we do know B, and we do know the angle C. So this is going to work. We have an equation with one variable. And I'm going to save you guys the time and the trouble. If I solve this thing, I get 6.529. So side C is equal to 6.529. I actually want to continue to solve this triangle because there's one other thing that comes up in solving triangles that I think this problem does a good job exemplifying. So here's our triangle. We want to finish solving this. We want the other angles. We have all three sides. We want the other angles. Okay. So what do we need to do that? We need to either use the law of cosines and the law of sines. I'd actually prefer the law of cosines, despite what you might think. Let's go ahead and solve this with the law of sines. And let me show you a problem that happens. All right, this specifically comes into a problem when we have side-side angle. All right, that's what we have here. And we can use the law of sines with side-side angle, but it's dangerous. And here's why. All right, so there are two angles. let's solve for angle A. So sine A, we have its length, 11. And then let's go ahead and get, we have C, so sine 20 over 6.529. All right, if we solve for A, we get sine A is equal to, what's it going to be? 6.529, or nope, sorry. $11 divided by, divided by 6.529, sorry guys, with sine 20 on top. Yeah, that's right. All right, and then if I take the arc sine of that thing, I get, plug it into the calculator, 35.183. 35.183 degrees. And that is totally impossible. Think about why. All right, 35.183. Why is that not possible? All right, the reason is the arc sine function gives you angles between negative 90 degrees and 90 degrees. But this angle is obtuse. All right, it is opposite the largest side in this triangle, so it must be the greatest angle. All right, if this is 20 and this is something less than, I don't know, 70, then this angle must be obtuse. But 35.183 in general just feels wrong. It's so small. Right? The way you should solve triangles, if you so choose to use the law of sines and you're dealing with side-side angle, solve for the smallest angle first. Because in a triangle, two of your angles must be acute. So if you have 20 here, if you use the law of sines, this will be the correct angle. The calculator will output the correct angle because this is acute. It's less than 90, and the law of the arc sine function will give you the correct answer. However, this is obtuse, and we've been given the wrong angle. All right, how do we deal with this? All right, this is not A. A is 180 minus that, right? Pi minus, as I say very often in class, 35.183. Cool. All right, and what is that? That is 144.817. Right, this is 144.817. And because of that, this is 15.8184. Right, that's the triangle sum theorem. These sum to 180 degrees. However, I highly encourage you to either use the law of cosines. Law of cosines will give you something between 0 and 180. It will always give you the correct answer. Right, but the law of sines only gives you the correct answer if the answer is acute. So be careful. And with that, I got one last example for you. It is if given side, 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 will the law of cosines work for us? Let's go ahead and say like 9, 7, and 5. All right, this is not a Pythagorean triple. This is not a right triangle. Let's go ahead and call this right here B. No, sorry. I'm looking at my example in my packet. This is 9. Let's call this thing A. This is 5. Let's call this thing C. And let's call this thing B. Cool. All right, so can I use the law of cosines here? I cannot use the law of sines because I do not have a pair of angle and opposite side. But I can use the law of cosines. So we have, let's just pick an arbitrary one. Let's go for angle A. So I want cosine A. All right, so that means I need B and C here. I need a B here, a C here, and an A here. And then I have everything but the angle A. This is good. All right, so I have 9 squared equals, what is this going to be? 7 squared plus 5 squared minus 2 times 7 times 5. Let me tell you this, the biggest mistake I see from students is forgetting this too. Don't forget. And then cosine A. And if you work through this, you're going to get cosine A is equal to some number, right? Cosine A is equal to, let's see, it's going to be 7 squared plus 5 squared minus 9 squared all over 2 times 7 times 5. I believe that's correct. Boom, 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 boom. Yep, that's correct. And that's what cosine A is equal to. So when you take the arc cosine, you will, in fact, get the correct answer because arc cosine spits out things between 0 and 180. So this will be the correct answer. And that answer ends up being 95.739. All right, so if this is 95.739, I'll leave it to you guys to, that's a 7, that's a 3. I'll leave it to you guys to find these two last angles, either using the law of sines or the law of cosines. Again, it's up to you. I'll tell you what they are, though. B ends up being 50.70. That's a 7-0. And this ends up being a 33.557. Cool. All right, and there's your completed triangle. The law of sines or the law of cosines will work for these last two. They're both acute, so you don't have to worry about getting the wrong answer with the law of sines. The law of cosines will, in fact, always give you the correct answer because it spits out 0 to 180 degrees. All right, I got one last one for you. And this is my favorite one because it's super duper hard. All right, I have the problem where A is equal to 10, B is equal to 12, and C is equal to 25. Go ahead and do this problem. This one is just the worst. Just kidding. All right, so this actually brings up a really important topic, and that is the triangle inequality. All right, within a triangle, A plus B must be bigger than C, and 10 plus 12 is less than 25. So this triangle here looks like this. All right, this is 25, this is 10, all right, this is 12. There's no triangle here. All right, so when your teacher said side, side, side makes a unique triangle last year, there was a caveat. It must satisfy the triangle inequality of A plus B is greater than the hypotenuse. Or I guess not the hypotenuse, that'd be the wrong term. A plus B, two of the sides must always sum to larger than the third side. All right, so hopefully you didn't spend too much time doing this problem because there was no solution. Gotcha. All right, so there you have it. I think the most important thing in this video is this best proof of the law of sines. All right, the law of sines doesn't just equate the side lengths and angles. It also is the diameter of the circumscribed circle. But we also got the law of cosines in here. We got a bunch of examples, and I think just becoming good at it comes from practice when it comes to the law of sines and the law of cosines. So I'll throw some practice problems at you guys. But with that said, I'm going to close it out here. There you go.